All right, hi. So today we're really excited to have Zun Li, who is a fifth-year PhD student in computer science at the Strategic Reasoning Group at the University of Michigan. He's advised by Professor Michael Wellman. In summer of 2022, he worked as a research scientist intern at DeepMind Alberta, blessed be its memory, mentored by Dr. Mark Langto. He completed a bachelor degree at Shanghai Jiaotong University, majoring in computer science, where he was a research assistant at the Advanced Network Lab. I think this is kind of really exciting work, bringing forward a lot of directions that have kind of been emerging in the field. And yeah, so we're really excited to have you, and I'll pass the mic over to you and mute myself.
Yes, thanks, Eugene, and thanks for inviting me to give this talk. So I'm happy to talk about our work combining tree search, generative models, and the Nash budding concept in game-theoretical RL. And this is a joint work with my collaborator at DeepMind during my internship. So in recent years, we have witnessed tremendous progress in computer game AI. We have people have built human level or even superhuman level AI in Go, poker, and recently in diplomacy. And I believe there are two main algorithm techniques that underline the success of these bots, which are deep reinforcement learning and search. So on one hand, deep reinforcement learning is very good at training quality value function and policy function, leveraging the expressiveness of deep neural nets that can generalize well across large state space. On the other hand, search techniques such as Monte-Carlo Tree Search or counterfactual regression minimization with subgame resolving, they can leverage computational power at decision time to improve the strength of the blueprint policy, and usually they can improve the strength to a large degree. So here I just want to highlight some example architecture that was adopted in previous bots. The first one is AlphaZero, which is the general purpose algorithm that combine deep IO and MCTS for large adversarial perfect information game. And AlphaZero has produced superhuman level AI bot in Go, chess, and Shogo. For large adversarial imperfect information game, the architecture rebuild and the playoff games combine deep IO with CFR and have demonstrated success in domain like poker and Scotland Yard. And recently we have seen a tremendous progress in diplomacy, and the researchers from Meta AI proposed the architecture DORA, which I believe later evolves into the CSIRO architecture. And the DORA is architecture that combines also train deep IO and use one step forward Nash Q learning as the search algorithm. So I believe, so these are the example architecture, but I believe more or less all these architecture originate from AlphaZero. So in the next slide, let me just recap how AlphaZero work, and that will be serve as the building block of this talk. So AlphaZero, it turns out AlphaZero is a very neat architecture that combine the power of deep IO and MCTS. It designed the training loop in a way such that it will first train a policy and a value network using the self-play trajectories generated by Monte-Carlo Tree Search. So in this trajectory, the MCTS will first produce, at each decision point, it will produce a policy target, which will usually be the visiting frequency during the search at the root node, here, which is pi. And also it will take an optimal action, which typically will be the action receive the maximum visit count during the search. And also it will use the return at that trajectory. Here it is Z. So MCTS will produce the data pi and Z to train the policy and the value net by minimizing this loss function. And then every several number of epoch, the updated deep IO network will further guide the search procedure of MCTS. So the policy network will guide the action selection procedure for those expanded nodes within the search tree, and the value network will truncate the unexpanded node on some depth limit. So in a nutshell, AlphaZero designed the training paradigm in such a way such that the component of deep IO and the component of MCTS will just reinforce with each other and produce more, so that it will produce more and more competitive agents. But here there are several issues about AlphaZero. So first, AlphaZero uses Monte Carlo Tree Search, but MCTS is really an algorithm that is specifically designed for perfect information games, because each node of the search tree just represents the full world state that is assumed to be fully observable. The second problem is AlphaZero is trained entirely through self-play, which means it generates the IO trajectory by playing against a copy of itself. But as was pointed out in previous work, self-play is usually limited to several settings. So first, self-play is limited to two-player zero-sum games, because in self-play, you are training with your training partner, but your strategic behavior could be just overfit to that training partner. So in two-player zero-sum games, this overfitting behavior is okay, because in game theory, there is the theorem that every equilibria is interchangeable. But for general-sum games, that could be a problem, because if you are compete with an unseen opponent at test time, the self-play behavior may the self-play maybe just lose the generalization capability. And also in previous work, it has been pointed out that self-play training is good at exploit those games with large transitivity components, which means there is some maybe some clear relative order among the agents. But for games with, say, large rock, paper, scissors component, self-play maybe is not the best way to train the agent. So in this work, we aim to address the previous issues. So first, we want to extend the AlphaZero style search algorithm to games with large imperfect information. And second, we want to, instead of using a self-play training outer loop, we want to utilize a population-based training that we consider is more suitable for general-sum games. So next, before I get into the technical detail, let me first introduce the domain we want to solve, the game we are interested in. So the game we want to solve is the so-called deal or no deal bilateral alternative bargaining games. So this is a game model that in recent years that is popular within the natural language processing community and also in the multi-agent emergent communication community. But this is really a game model that is originated from the classical economic literature. And it is also served as the fundamental model for the automated negotiation computation. So here is how this game works. So the goal of this game is, so there are two agents and there is a set of resources. And each agent have different private valuation towards different kind of resources. So for example, here player one, it values one book for 6 units of values, and it values one hat for pure unit of values. And also player 2 have different variation towards different kinds of good. So, and also this game kind of constrain the validation such that, say, if player 1 get all the items in the item pool, then the total utility will be 10. And it is just a normalization factor. So, so how does this game work? So first, the validation factors and the resources will be drawn from a common knowledge distribution. So the configuration of the resources. So for example, here there is 1 book, 2 hat, and 3 basketball. This will be fully observable for every agent, but the validation are totally private to every agent themselves. And then the agents will just alternatively propose offer and counter offer. Well, the offers are just a plan to how to divide the set of pools. So for example, here player 1 proposed an offer. It wants to get 1 book and 2 hat for itself and the rest for player 2. And then player 2 just reject this offer and propose another plan. So player will just keep doing this offer and counter offer proposal until an agreement is reached or a maximum number of rounds is reached. And towards the end of the game, if there is an agreement, then the player will just receive the payoff accordingly. And if there is no agreement, then everyone just receive 0 utility. So as we can see, this is a game of general sum and imperfect information elements. Well, here the players are not adversary. They want to come up with an agreement that it works for everybody. And also the imperfect information is the validation of your opponent. That is very crucial during the strategic reasoning process. Okay, so yeah, if there is no question about how does this game work, I will just get into the first technical part, which is how to generalize the AlphaZero style search to imperfect information game. So it turns out the idea is very simple. So instead of using MCTS, we will resort to another MCTS style algorithm in partially observable domains called Information-Set MCTS.
Quick interruption.
Sure.
There's a question asking if there's a discount, if the game is discounted per round or...
Yeah, great question. So in this work, we did not consider discount factor, but we are currently working on adding more experiments using discount factor or probability of ending in each round. But in this work, we did not consider discount factor.
Okay, cool. Thank you.
Yeah. Okay. So yeah, let's get back to IS-MCTS. So so what makes IS-MCTS different from MCTS is first, each search node of the search tree represent an information set or the action observation history of the search agent. And also the root of the search tree is actually a belief state, which is an information set paired with a distribution over the actual world state. And the way that IS-MCTS goes is in each search round, it will first sample an actual world state from the root belief distribution. And then it will just conduct what the vanilla MCTS will do, like simulation, tree backpropagation. And then all the statistics will be aggregated on the information set level, like the visit count or the Q values. And this is not a new algorithm. Actually, previous work have already studied this MCTS algorithm in partially observable domain. I just want to point out that the first of this class of algorithm is PONCP, stand for partially observable Monte-Carlo planning. And in PONCP, it uses particle flirting to represent the belief state at the root of the search tree. And then it is the first IS-MCTS paper. And in this paper, they use a uniform distribution over the world state to represent the belief. And you can see this is actually a very rough approximation of the belief state. But in that paper, they show very good empirical results. And another work I would like to mention is the so-called ABR, or stand for approximate best response paper that is published by fellows at DeepMind Alberta. And in that paper, they just compute the exact posterior belief to represent the belief state. And the way they compute this exact posterior belief is just to reweight the distribution by the action probability along the history. But I just want to point out that among those papers, ABR is the first one that combined DeepRL with IS-MCTS in the same way that AlphaZero combined MCTS with DeepRL, which it trains the policy network and the value network. Okay, but in this work, we are interested in to handle not only to handle games with imperfect information, but we want to make our algorithm can handle games with large imperfect information. And the previous approach, such as particle filters or compute exact posterior belief, may just not be tractable for large imperfect information. Yeah, I hear there is a question.
Yeah, I have a question because I actually haven't read the IS-MCTS paper yet, but I will after this talk. Is it sound in the sense like, the actions you take influence the posterior computed by the other agent?
That's right.
And so does it account for that step of the process?
That's right, because so in another way, the posterior belief of the search agent depends on the action taken by the opponent. So it is just like each node within the information set represents, say, a particular validation vector of your opponent, and that belief will be affected by the action taken by your opponent.
Yeah.
Yeah.
Okay. Sure.
Yeah. Cool.
Thanks.
Yeah. Yeah. Back into the how do we deal with the large imperfect information? So in this work, we train a deep generative model G to represent the belief state. And furthermore, we are going to train this deep generative model G in the same way that AlphaZero trained the policy network and the value network, which we just use the information state data distributed within the RL trajectories to train the deep generative model. So it is just like when the MCTS algorithm are producing the trajectory, it will send the information state data to the deep IO network. And by minimizing some loss function, the quality of the generative network will improve. And then after every epoch, it will just replace the deep generative model with the latest version. And then it will just improve its quality along the training procedure. So for example, in the deal or no deal domain, the input of the generative model is some representation of the information set. And the output is some representation of a distribution over your opponent's value vectors. Okay, so if there is no question about how does this work, I will next present some empirical results. So here we just test the performance of the new search technique as the best response method against different kind of opponent. And particularly, we are test the search method with different generative models, and we use DQN as the baseline method. So first, let me expand the different generative model we are testing on. So here, simple learn just refers to the one that we are training the deep generative model. The exact generative model just means in each time we are computing the exact posterior belief. And this is in principle the correct way that we should do during the search procedure. The search generative model is called cheat. So cheat means at each time it will always sample the ground truth word state at that trajectory. But notice that cheat is a reasonable generative model at test time because usually we cannot know the word state. So here cheat is just, we use cheat just as a upper bound to show the upper bound of the search performance. And bad 1 and the bad 2 are just some arbitrary generative model that always sample the first index and the last index legal state. And finally, the uniform just uniformly sample over all the possible legal state. So here we just test the performance against 3 different kind of opponent. The first is random opponent, which is just agent that just uniformly play among all the possible legal actions. So here what we can observe is all those search-based methods immediately get very high best response performance, while the DQN agent needs to a lot of IO trajectory to match the performance of the search algorithm. And I believe that this validates previous observation that search really improve or have large, strong performance compared with plain deep neural network.
There's a quick question from
Sure.
Alexander. Do you want to just unmute and ask your question?
Yeah, sure. My first question is whether you're considering the entire history of play when you form your belief, like with an RNN or something like that. My second question is whether you expect this to scale to more than situations with more than 2 players. I guess one of the concerns being like the estimator of like sampling states and doing the rollouts might have like very high variance.
Yeah. So for the first question, so yes, we are the inputs of the network are some representation of the information states, which do consist of all the action observation history of the search agent. And the second question is about the scalability towards multiplayer games. So in this work, the way that we deploy search is mainly as a single agent search best response in the whole framework. So I believe in single agent, this is just a vanilla MCTS procedure. So yeah.
Okay, but I mean, doesn't the belief space grow a lot larger once you add more players?
I see. That's right. So I believe this is a problem of I think this relies on the capability of these deep generative models. So if the belief states are growing, then what we expect is the deep generative model can still learn some representation of the large belief space. So I think it relies on first, for example, how do we represent the input and the output of the deep generative model. Also, we can, for example, modify the architecture of the deep networks so that it will be more generalizable.
I see. Thank you.
Yeah. Okay, so just get back to the empirical result. So another observation we can make is as the opponent become more and more rational, the difference between different generative model will become more and more large. So for example, let's take a look at the DQN random BR opponent, which is a DQN agent itself is trained as the best response against a random opponent. And also here, the DQN self-play opponent, which means we are training QDQN concurrently until convergence. So the observation is, first, the best performance, perhaps without surprise, is given by the exact generative model and the cheat generative model. But what is really exciting is the simple learn method, which is the brown line. Its performance gradually improve its departure from the uniform generative model and gradually match the performance of exact and cheat as it is trained on more and more IO trajectory. So I believe this result really demonstrate that learning the belief state using deep neural network along the search training procedure really work, and it can even match the exact posterior belief. And also we can see the best that the DQN agent can do is maybe just match the uniform generative model, but it just gets stuck. Yeah, there's another question.
Yeah, I have an annoying question that I frequently ask. Do you have a sense of what this looks like on like wall clock time? So instead of training episode, because search is expensive, right?
That's right. So yes, in terms of wall clock time, I believe search will consume much more real world time than the DQN agent. For example, maybe it only takes 1 hour to train the DQN, but it may take, say, 5 hours, several hours to train the search agent. Yeah.
Okay, cool. Thanks.
Sorry. Yeah. Okay, so yeah, that mainly concludes the first part about how do we generalize search. And if there is no question, I can move to the second part, which is how do we replace the self-play based training? Yes, question.
I do have one more question.
Sure.
So there's this thread of like learned belief search that folks do in like Hanabi and things like that. And I'm curious if you can like kind of compare and contrast to you know, what folks do in Hanabi if you're familiar with it.
Yeah, sure. I did read this learned belief search and belief modeling in Hanabi. So if I understand correctly, the way that they train this generative model is by using the data from different self-play trajectories, and they expect the belief the generative model trained by this self-play trajectory will generalize well against general cases. But here in our cases, the way that we train this generative model, first we are fixing our opponent, and that will mathematically, it will just induce there is some correct belief distribution out there. And here, what we do is we just want to use deep generative model to approximate that correct exact posterior belief. So I believe there is some maybe the purpose of this work are slightly different, but yes, I believe our deep generative model is to some extent related to how does this Hanabi work train the generative model.
Okay, cool. Thank you.
Yeah. Oh, okay. So yeah, next, let me get into the second part. So, so here, instead of using cell play, we want to use a population-based training framework to train our agent. And particularly in this work, we use policy space response oracle as the outer loop training algorithm. And I believe many of the audience have already been familiar with PSRO, but let me just recap PSRO again using some terminology. So the way that PSRO works is it will maintain a set of strategies for each player, and it will iteratively enlarge such strategy set by compute a sequence of single agent IO problem. So let me just give an overview of one iteration of PSRO. So let's say in the current PSRO step, we have 4 strategy for each player. And actually that four strategy for each player, actually it will define a normal form game model. And then we can simulate a game matrix or game tensor by just comparing, by just computing the payoff of every possible joint policy in the policy pool. And then typically what people will do is they will compute an empirical equilibrium on this empirical game. And people usually call this this procedure of computing equilibrium the meta strategy solver step. So for example, we can use Nash equilibrium or correlated equilibrium as the meta strategy solver. So the meta strategy solver step will just produce a probability distribution over the policy, the strategies. And then we just enumerate every player and we just assume the opponent will fix to this opponent distribution. Then we will just result to some reinforcement learning algorithms such as PPO or DQN to compute a best response against this distribution. And then in the next iteration, we will just add this best response strategy into the strategy set. And then the process will just iterative again and again until, say, a maximum number of strategy or a quality equilibrium is found. Okay, so yeah, in previous work, people have there have been tremendous research work done on PSRO, and people usually consider a purely adversarial domain and use purely non-cooperative game solutions such as Nash equilibrium as the meta strategy solver. But in this work, we want to propose several new meta strategy solver that is actually come from the cooperative game theory domain. And particularly in this work, since we are interested in negotiation game, we just grab a notion called Nash bargaining solution to design a new solution concept. So in a nutshell, what NBS does is it will find a strategy profile that maximizes the product of agent's utility. which is very simple. And if all the possible payoff that the agent achieve is a convex set, it has been proven in economic literature that the Nash bargaining solution will pick a point lying on the Pareto frontier of the payoff set. So in this work, given a game matrix or a game tensor, how can we compute MBS? So what we propose is we propose a very simple project gradient ascent algorithm, which we are optimizing over all the possible mixed strategies or correlated strategies. And each those mixed strategies will corresponding to a particular point in the payoff space. And we just apply, we just iteratively do the gradient ascent and then project back to the simplex space. And then we report the last iteration mixed strategy to find the NBS. And and we have some theoretical results, which just basically said the convergence rate is 2 to the minus 1/2, and it is a last iteration convergence, which just by applying the standard optimization analysis. Okay, so here we just want to investigate the effectiveness of NBS as a meta-strategy solver in PSRO. So what we did is we consider another domain called colored trails, which is also a class of negotiation game, and the colored trails is was a very popular domain that is very particularly popular within the arts community. So the way that color trails goes is, so we have some number of agents, and the goal of these agents is to reach some destination point from their starting point on the grid world. And at the beginning of the game, each agent will be given different colors of chips with different amounts. And on each, every agent needs to select a path from its starting point to the destination point. But on each location on that path, the agents need to pay 1 unit of chips of the corresponding colors. So the goal of this game is just to let the agents negotiate and exchange different number of chips such that they will find a suitable path towards their goal. So actually, color trails have many parameters, and there are also many details that I didn't cover. But one thing that is good about color trails is that it turns out in this game, we have a practicable characterization of the Pareto frontier in the utility space. So what we studied is we just test the performance of PSRO plus this MBS-based meta-strategy solver in terms of reducing the Pareto gap. So what we did is we just use Boltzmann DQN as the best response method, and we test different meta-strategy solver and compare their performance. Well, here the y-axis is the L2 distance to the Pareto frontier, while the x-axis is just the PSRO iteration. So basically, our conclusion is the best performance are given by the NBS meta-strategy solver, as well as there is a so-called social welfare meta-strategy solver, which is a solver that always pick the entry that has the highest social welfare within the empirical game matrix. And in the right figure, we just plot one example trajectory while the PSRO approach the Pareto frontier.
What about that plot clearly indicates that it's at the Pareto frontier? Just trying to follow the plot.
You mean the right figure?
Oh, yeah.
Yeah, so I think it basically said along the PSRO iteration, it's just it reduced its distance to the Pareto frontier. So as you can see, maybe in the first few iterations, it cycles around some region, but gradually it gets closer to the frontier.
Got it. Thanks. And Lucia has a question, and Kevin has a question.
Yeah, sure.
Lucia, if y'all just want to unmute yourself to ask in order. And
hello, I wanted to know, when you apply the Nash bargaining solution, usually my understanding is that, yeah, for Nash bargaining, you have theoretical guarantees in the literature for two agents. So my first question is like, I didn't understand if you apply to more agents. And then second, when you converge to the optimum, in how many bargaining rounds? Thank you.
Yeah, sure. So I believe the theoretical guarantee you are referring is like the Pareto optimality, and also other things like I don't know, symmetry or something like that. So in our cases, so first, if I remember correctly, the original theoretical guarantee of Nash bargaining solution doesn't limit it to two-player cases. I believe as long as the payoff set are convex and also it satisfies the several axioms such as symmetry, invariance, that was in the original NBS paper. I think the theoretical guarantee holds for arbitrary number of players. That is my reflection. And in our cases, in terms of the convergence guarantee, so PSRO is designed for large stochastic game, while the number of policy is enormous. So I think what the best we can show is just show empirically how does the Pareto gap reduce along the training iteration. But in principle, we need to enumerate every policies within the stochastic game. That could be very intractable. So I believe that is one flaw of PSRO. But what people usually found is empirically it's reduced the gap.
And do you converge to the solution in one round? How many bargaining rounds do you need?
Sure. Actually, let me clarify the convergence you are referring to. So are you referring to the whole PSRO plus NBS framework, or only the, say, the NBS, the project gradient ascent algorithm? That
One, yeah, thank you.
This one, okay, cool. Sorry, I misunderstood. So yeah, for that one, we have this result, which basically showed the convergence rate is t to the minus 1/2.
Okay,
so it is just like at iteration t, the gap between our last iteration result to the optimal result is bounded by t to the minus 1/2.
So that if agents bargain for 100 rounds, that means it takes what is the square root of t to converge in the number of bargaining rounds?
I see. So actually, here the project gradient ascent is just a purely optimization process. So like each gradient ascent does not necessarily corresponding to a bargaining instance.
Okay.
So what we did is we just take a game matrix and then we apply this gradient ascent algorithm on it. And each entry of the payoff, the game matrix corresponding to one particular bargaining instance, but we assume that is already computed before.
Okay, thank you.
Yeah, cool. If we can move on to Kevin's question, just to like give some time for the rest of the talk to finish.
Sure.
Thanks for the questions, Lucia.
Yeah, I just had a really quick one. I was just so you mentioned on that slide there are like two lines. One is like the MBS, and then one was like welfare maximizing. Just to clarify, the welfare maximizing is also is that also something that the MBS could output, or like the MBS you said it outputs something on the Pareto frontier, but like the welfare maximizing would also be on that frontier, right?
Yes, that's right. Because what social welfare did is you just plot the line y equals to x, and I believe the intersection between this line and the Pareto frontier would be the social welfare one.
I see. So like, is there any reason to believe that like social welfare that solution wouldn't be as good as the NBS one, or like would you expect them to kind of do the same?
Yeah, I believe in principle they are both some way to reach the Pareto frontier. And in terms of which one is better, I believe maybe it is a very empirical question. So I believe, yeah.
Thanks.
Yeah, okay. So yeah, maybe let me move forward to the most important part of this work. So we have already talked about the new search technique, and we have talked about the PSRO framework. So finally, what we did is we just combine everything together and build a general purpose training algorithm that we consider is suitable for general sum imperfect information domain. So basically what we did is we just use this new search technique, this IS-MCTS technique, as the best response method within the PSRO loop. So it is just like in each iteration of PSRO, we use this MCTS procedure to train against a distribution over opponent, and then we add the whole tree search algorithm in the strategy pool. So using a new best response method in PSRO is not so interesting, but I believe what is actually interesting is the interpretation of building MCTS in PSRO. So just recall that the way that we do best response in PSRO is we have compute a distribution over opponent, and then we just do IO compete against it. But if you think about it, if you are doing MCTS against a distribution over opponent, it is actually effectively doing a PON-DP planning procedure, while the hidden state of the PON-DP is both the actual world state as well as the opponent's pure strategy choices in the game. Because the meta strategy, the distribution sigma minus I actually introduce new incomplete information of the game. So let me just try to visualize the correct way to do the search. So let's say we are search against a distribution over opponent sigma minus I, and open reach a new information state S. The correct way to do the search is as follows. So first, we need to sample an actual world state H from the generative model G. And given H being reached, we should actually infer a posterior distribution over the opponent pure strategy policy. The reason is because if we assume that the current history is H, then the likelihood that the opponent playing each strategy will definitely be shifted according to the action that it takes along the history. And then we just sample a new pure strategy profile from this posterior mixed strategy. And then we just replace the opponent node with that sampled pure strategies. And then say, upon reach a new information state S prime, we will just do this Bayesian inference again, and then just output the optimal action. So what I found really cool about this Bayesian interpretation is that actually, if you think about it, what PSRO really did in our framework is it will generate a diverse type of the opponents purely using deep RL. And then during online decision making, we are actually inferring the likelihood of the opponents belonging to different types in an online fashion. And also this type-based reasoning was also very popular in previous work like ad hoc teamwork or even in Hanabi, I believe. But here we just generate the type purely by exploiting the PSRO framework. Okay. Can someone remind me how many minutes do I left?
There are 3 minutes remaining.
Okay, cool. So let me just quickly get through the remaining text. So we have introduced the whole training loop, and the outcome of our training loop is a strategy set for every agent and the distribution over these agents. But the question is, if we want to say deploy an agent against a human, what kind of agent should we extract? So basically, there are two approaches. The first is just we just take the sigma I computed by PSRO and apply Kuhn theorem in extension phone games and just play that meta strategy at test time. The second approach is we pick the opponent strategies generated by PSRO and assume the opponent at test time exactly playing the meta strategy sigma minus I at training time generated by PSRO, and then we just use MCTS to search against to do this Bayesian posterior procedure and search against it. So the final experiment is we just test the performance of our PSRO agent against human. So what we did is we recruit about 350 human participants, and due to limitation of the infrastructure, each participant can only play 5 matches against our agent. So what we did is we just select 4 different PSRO agent and one agent that is trained through self-play DQN. And then based on different selection criterion, we finally select 2 most competitive PSRO agents, denoted at C1 and C2. And we select the most cooperative agent and the one that is we consider is the most fairness agent. So the final result of the human study is summarized in this table. And let me just quickly expand what does it mean. So each row of this table represents one agent, the performance of one agent. And the first column is the average payoff of a human against of our agent. The second column is the average performance of an agent against human. The third and the fourth column are basically the summation and the product of the first two columns. So the first observation is that if we only care about individual reward, then independent DQN achieve the highest reward for itself. But we can see that it achieved that by beating the human a lot. So independent DQN really plays very aggressively. But we found is the cooperative agent and the fairness agent trained using PSRO get higher social welfare and higher the Nash product. And moreover, the fairness agent achieve higher average human payoff by giving up to human to some extent. And just as a baseline, the average human versus human average payoff is like about 6.93. And we consider our fairness agent, its confidence interval is overlapping with the human versus human performance. So we consider some of our agent is very close to human performance. Yeah, so yeah, that is basically the experimental results. So yeah, maybe I will just end here. And if you guys have more questions, I would like happy to answer.
Okay, thank you. Thank you so much for the great talk.
Yeah.
Do a little weird applause. I am going to turn off the recording now,